Okay. So here, we have this new thing over here. So far, we've seen for loops, but now we have this while thing over here. Well, if we look at what this actually does, so x is 10 raised to 9, while x is greater than 0, what we do is we print x, then divide x by 2. So what we see here is we start at 10 raised to 9, then we keep dividing by 2 until we reach 1 over here. So this is what we call a while loop. So for a while loop, while the condition you put here is true, so while x is greater than 0, it's going to execute everything that you put inside of the block here. So it will do something while some condition is true. Okay, so you can think of this as an if statement that goes over and over again. Okay, so just like with for loops, this is imperative. So you usually use while loops if you, alongside other kinds of imperative concepts. Okay, so why do we even have while loops if we already have for loops? Well, while loops are useful if you don't know when your sequence is going to end. For example here, we don't know when 10 raised to 9 is going to reach 1 like this, especially for bigger and bigger numbers. So if we don't know how long it will take for our sequence to go through all of these values here, that's when the while loop can be useful. Okay, so another example is this. So if you're familiar with the Collatz conjecture, it's basically something that says that if you have some number and you keep applying this function to that number, so let me write this function first. So if n is even, you divide the number by 2. If it's not even, you return 3 times the number plus 1. And the conjecture is, no matter where you start, if you keep calling this function again and again, so n is equal to Collatz of n. So let's say I do that, then I also get the value here. No matter where I start, or for which number I start, I will always eventually reach the number 1. So after many iterations of this, I will eventually reach the number 1 like this. So for here, we want to show all of the numbers that we get if we start from some specific number n. Okay, so for 7, we have this sequence here. For 100, that's the sequence I just showed over here. So all of these numbers here. So how do we actually show all of the numbers that appear? Well, what we basically have to do is, while this n is still greater than 1, we keep applying this function. So what you can do here is print n first, then print n, then apply the Collatz function. Then if n is already 1, that's when we're done. So to write this as a while loop, what we can do is, while n is not equal to 1, or you can also say greater than 1, what we do here is print n, then apply the function to itself, Collatz of n. So if we have this function, then we give it 100, that will give us all of the values we saw a while ago. At the end here, we can also print 1 if we want. So doing this again will now give us everything, including 1. So that's how you would use a while loop if you don't know how many iterations you're going to need. Okay. So we made this sequence. If we have 7, this is going to be noticeably longer compared to something like 8. So this is a lot longer compared to this. So that's when while loops can be very useful. Okay. So this is one way to do it. Here it's making a list, and you have something like this. If you want to make a generator version, then all you have to do is put yields instead. So for our implementation, what we can do is put a yield instead, yield n, then yield 1. Then what we have here is, if we have list, then show collapse of 100. This will now give us a list containing all of the values from a while ago. So this is the generator version. Okay. So this is some other version. So here, what's happening is there's yung condition that it uses for the while loop is just while true. So true is always true. So what that means is, if you have while true, then you have something over here. This is never going to end. So let's say I print something. This is going to keep going forever. So this is what we call an infinite loop. Be careful about accidentally making infinite loops. So in order to actually stop a while loop, another thing you can do is to use this break keyword over here. So what is that actually doing? So break, as the name suggests, stops the for loop, the while loop. So here, let's go back to our example a while ago. If I replace this with true, what I can do here is, if n is equal to 1, I want to get out of this while loop. So I can break out of this while loop. So I can do the same thing again. List show collapse of 100. Oops. And if I do that, I'll still get the same list. So break is another way to stop a while loop, aside from the condition becoming false. Okay, so while true is an infinite loop, and break exits any loop you give it. So our advice is only use break if you really need to. If you already know what condition you want, then use that instead of an infinite loop like this. Okay, so other use cases is something like this. So here, I'll have a while loop that takes in as input. Don't type exit. So this will give me a string depending on what the user gives me. So while this is not equal to exit, then here, let's print out something like this. So here, I'm going to get a prompt from this input function. So hello, that will give me this iteration here. Then this will keep going until I actually type out this specific string. So no matter what I type over here, this loop is going to keep going on and on. So until I write exit like this is when yung while loop will stop. So you can also use a while loop if you're handling input like this. Okay, so actually, this interactive mode that I have, whenever I run Python 3, this is technically a while loop already. What's happening is Python is printing out these 3 arrows over here. Then I type something here. Whenever I type something, Python responds with whatever value that corresponds to. Then it gives me another thing to input. So whenever I give it a value, it evaluates that value, then it moves on to the next prompt like this. This is what we call yung REPL. Yung read, it reads input from the user, it evaluates that input, then it prints out what it evaluates. So read, eval, print loop. Okay, so what if we actually want to, let's go back to the example here. What if we want to get the command that the user actually put here? So how do we do that? Well, one way is we can have s is input, don't type exit. Then here, we can have some string. So this now gets assigned to the s variable over here. So while s is not equal to exit, we will get the value of s again. So s or print you type s. Then it gets the value of s again. Don't type exit. So some while loop that looks like this. So you type some string. If I put another string here, it now knows what value I gave as input. So I keep doing this until I actually type the string that makes the while loop exit. So this is one way we can actually capture the value that we get from input. Okay, so that's one way. Another way is, so this is what we did. Another way is, well, if we notice what we're doing here, we're typing this line explicitly twice. One here, and one inside the while loop. If you want to avoid doing this, what we can do is something like this. So s gets assigned to this thing over here. And here inside, I can now put u type, then s. So here, I can now capture the value I'm getting from the input over here. So this syntax over here is what we call an assignment expression. It's an expression where the value gets assigned to this variable over here. And this operator, this colon then equals, this is what we usually call your walrus operator. Since if you squint hard enough, this looks like a walrus. So this is how you can avoid the duplication over here. This duplication. Okay. So when it comes to while loops, since you don't know when it's going to end, it's very possible that you accidentally make an infinite loop. So it's not that hard to get yourself into an infinite loop. So here, if we think about this while loop over here, this is kind of equivalent to this recursive function over here. So this is your condition, and this is your current state. So here, if you no longer satisfy the condition, then you just return the current state. Otherwise, you still have to do this again. So another iteration of the while loop. And this is how you update your current state. So if this is how a while loop works under the hood, then what that means is you don't really know. The point of a while loop is we don't know when this condition is actually going to be true. So it's hard to actually implement this condition function over here, whatever it is. So because this condition can get very complicated, And for example, for the collapse example a while ago, in order to figure out when this actually ends, we need to prove an unsolved problem first. So this conjecture is, well, a conjecture. So no one has actually solved it yet. So proving this condition can be very hard. And aside from hard stuff like this, it can also happen accidentally. So let's say I have this example here. This is very similar to the first while loop we had a while ago. So x is 10 raised to 9. So while x is not negative, we print x, then we divide x by 2. So this is very similar to our while loop a while ago. If we try to run this, we'll see that we get a bunch of zeros. So what's happening here is, if we look at the while loop again, since this is greater than or equal to 0, what happens here is, if I run this then stop it immediately, it's too fast. So what's happening here is, it does do all of the division from a while ago. So it starts at 10 raised to 9. Let's say x is 10 raised to 9. It does start at 10 raised to 9. Then eventually, once 10 raised to 9 goes all the way down to 0, that's when it keeps printing out 0 like this. So this is an infinite loop, so be careful about that. So whenever you make a while loop, it's very important that you know for sure when this condition actually becomes false, or you know that this will eventually become false. Otherwise, you will run into an infinite loop. Okay, so one main tip you can use for this is, if you want to negate some condition, the opposite of less than or equals is greater than. So if you want to negate the condition x is less than or equal to 5, you do not do x is greater than or equal to 5. Yung negation niya is x is greater than 5. You don't include the equals over here. Okay, so that's infinite loops. Okay, so let's now look at some more examples for loops and generators. Okay, so here I have a string and a bunch of other strings. We want the first one here that starts with this string here. Okay, so find first with prefix. I have a string and I have a bunch of other strings. So what we can do here is we look at each of the other strings here. So if s is a prefix, if is prefix s then other, then we already return that other string. Okay, so we need to implement is prefix over here. So we want to find out if given s and t, this will checks whether we want to figure out if s is a prefix of t. So there are several ways you can do this. One way is just by using standard comparison. So one way you can do this is, you know the length of s from length of s. If you slice t, if you get the first length of s characters of t, this should give you the string s. So something like this. So find first with prefix. Then here I have a, then a bunch of strings. So BA, CCA, then we have AA, then A. This will give me the first string that starts with A over here. So this is one way you can do it. another way is Python has a built-in function. So return t then starts with s. This is another way. So if we do the same function call again, this will still give us the same result. Okay. So this is another way to write it. Instead of returning already, you can break first before actually returning. So yung starts with is, as I mentioned, it checks whether this starts with this. So if you don't want to use break, you can also do the return directly, which is what we did. Okay, so if you want to raise an error, if there's no such word that satisfies this, you can always do that at the end. So here, not there, for the actual function, if you reach the end and none of the strings satisfy this, you can raise a value error and put your error message over here. So if we do the function call and we remove those, we'll now get the error over here. Okay, what else? So here, this is a slightly more clever way. Since what we really want is just a single element, the first element that starts with the prefix here, what we can do is we filter out all of the words that actually start with it, and we just call next a single time. So this is a generator that gives us all of the words that start with this prefix. Then next just gives us the first element in that generator. Okay. So here, if you want to catch if none of the words contain that prefix, what you can do is handle yung stop iteration. So the gist of it is, if none of the words here start with this prefix, then this generator is going to be empty. And if we call next on an empty generator, we know from the previous lecture that that will give us this error over here. So you can catch that exception. So try, then something here, then except stop iteration. Stop iteration. That's where we do the handling over here. Okay, so that's for this example. For this next one, we want to get the non-empty substrings. So we already went over this in one of the previous lectures. So non-empty substrings. So define non-empty substrings. The way we did this last time was we looked at yung starting and ending indices. So for example, return or for I in range length of s, then for j in range length of s, we can do something like this. So if I is less than or equal to j, we can print then s index from I to j. So non-empty substrings, or this is non-empty, so this should be less than. So non-empty substrings of, let's say, ABA, this will give us all of the non-empty substrings here. AAP, okay. So here, there are several ways we can write this. Why is this not returning everything? Print ij. Then we call that again. So here it gets these values. This should be length of s plus 1. Let's remove this. So this should be there. If we call this again, that should give us everything. There. So this is one way to write this function over here. Since this is a simple nested for loop, we can also use a comprehension for this. So here, what I'll do instead is return tuple, then s from I to j, for I in range length of s, for j in range length of s plus 1. 1, 2, there. Then we don't need all of these lines anymore. Then our filter is if I is less than j. So non-empty substrings of ABA should give us all of these values, but now inside a tuple. So that's another way to implement this. So if we want a generator instead, what we can do is for this part over here, for the implementation a while ago, what we can do is instead of printing, we can just yield s from I until j. So this will already work as a generator. So non-empty substrings of this now gives us a generator object. So simple as that. Okay, for this particular implementation, it uses this separate function. And this is also a generator. So it uses a generator here. And again, it's j plus 1, at least for this, since for slicing, this index is exclusive. Okay. So whenever we have something like this, so here, this is a generator, and what it's doing is for each element, it's just yielding. So you basically get each value here, then just yield it for this generator here. There's a simpler way to write this part over here. If you have some sequence that you want to yield from, then the shortcut for that is, well, yield from. So this is the generator you want to get values from. If you put that after yield from, this will behave the same way as this. So you don't need to explicitly write out a for loop anymore. So instead of writing a for loop where the body is just yielding, what you do here is you just use yield from, then the generator over here. Okay. So here, let's say you have this instead. This example, I have a function take that's a generator. If I give it a value as well as another generator, I should only get the first num values of this generator here. So one way we can do this is we only need to take the first num values. So while num is greater than 0, yield next of this, we're getting the next element of this generator, then we're yielding it. Then decrement this by 1. So if I take the first 5 elements of the numbers from 1 to 100, and I put that inside a list, that will give me, here, this should be a generator. So here, that gives me the first 5 values of this generator over here. So this is one way to write that. Oops. Okay, so this is one other way. Here, it's using a for loop instead of a while loop. So for n times, it's going to yield like this. Okay. So there's a slight problem here. If we're taking too many elements, so this is a lot longer than this sequence here, then in order to work around that, we have to handle, well, we have to handle short sequences. So this will give us a error, stop iteration. So how do we work around that? Well, one way is to explicitly handle yung stop iteration like this. So use a try except block. So this will solve this problem. If we add a try except block like this, try, then here except stop iteration, I'm going to break out already. So if I take the first 5 elements of this range, I only get the values that I can take. So this will solve this error over here. So there's another problem with this. For this example, the one we encountered a while ago. So what if I give this 1, 2, 3, 4, 5, 6? In that case, what we'll get now is a type error. So it's a type error because what's happening here is this next function doesn't actually exist for lists. Since, well, yung values of a list can be used any number of times. So there's not really any meaning to next like this. So this function cannot support lists. So the way we solved this a while ago is by wrapping this around iter. Another way to solve it is instead of wrapping the input like this in the actual function call, what we can do is in the function implementation, we wrap gen around an iterator. So we put the wrapping part inside the actual function, not in the function call. So here, for this case, if we take the same thing, 5 from 1, 2, 3, 4, 5, this will now work. Okay, so to handle non-generators, you add this line over here. Okay, so that's how you would handle these common issues like this. If you want to handle stop iterations, use try and accept. If you want to handle any kind of sequence, make sure to wrap it around iter. Okay. So these are more generator examples. So here, we already went over this a while ago. So I'll just use simpler examples for this. Let's say we have this generator that yields 4 values. And for value in f, I will print out that value. So we already know that this is a sequence containing these values over here. Now if I have this, remember also from the lecture a while ago that if I add stuff in between here, whenever it encounters a yield, it's going to pause there temporarily. So if I do this, print D, then print D, and I'm going to call G is F, then next of G. This will only do everything up until this point. Then same thing for the next few calls. So this pair, and so on until the sequence runs out. So that's for this example. For this, so here, the sequence of next is essentially the same thing as for name in members, or f is my generator. So for value in f, print value. So this will do the same thing. Okay, so this is what we just did. So again, as I mentioned in the previous lecture, you don't run the rest of the lines until you explicitly call next. So here in this for loop, this implicitly calls next in each iteration, which is why we see each of these chunks over here. So if you're using the next function explicitly, you have to remember that this will only advance every time you call next. So it will only print out some of these lines at a time. Okay. So this behavior, where it only prints out some of these lines at a time, this is what we actually call lazy evaluation. So in other words, generators are lazy. All of the other stuff that we've seen is done with eager evaluation. So the opposite of lazy evaluation. Okay, so the thing with lazy evaluation is that it allows you to do some nice things. So for example here, if I have a standard function which has an infinite loop, print hi, then it does something here. If I call that, I will get an infinite loop like this. On the other hand, if what I do here instead is a yield, this now becomes a generator. And we know that generators are lazy. So if I actually call this function, instead of running into an infinite loop, what I'll only get here is this same generator. So we don't run into an infinite loop if we do this. Okay. So if you use yield, you won't run into problems like this. Okay. So the only way that this definition will give you an infinite loop is if you actually try to iterate over everything here. So for x in f, ... that's when you will get an infinite loop. So generators give you a chance to avoid an infinite loop before you actually use the sequence that you want. Okay, so the nice thing with this is that if we have a generator, then we can use that in some of the other functions we had a while ago, just like take. So if you don't want to run into this infinite loop, you can write it like this. So take the first 5 elements of this infinite generator over here. Okay, so this is what we actually call an infinite sequence. So you can't just write your own infinite sequences easily. So even if you make this incredibly large, this is probably going to happen. So to make an actual infinite sequence, that's what generators are for. So if you have this generator here, and you use it properly, like this, you technically already have an infinite sequence. Okay? So that's another purpose of using generators. Okay, so this is an example for the Fibonacci numbers. This is a generator, so you can also use it like this. Take the first n elements of this infinite sequence. And yeah. So that's the nice thing about being lazy. You can technically make infinite sequences like this. Okay, so we'll stop here for now. Are there any questions so far?